everyone, and welcome to the Joy of Abstraction Book Club, Chapter 15. Thank you to everyone who submitted questions and to everyone who's following along. And thank you, as ever, to the Topos Institute and everyone there for helping with this book club and helping to run it. We've gone to 2 weeks per chapter, and I'm glad that that enabled some more people to send questions in. There's quite a lot of material in some of the upcoming chapters, so I hope that gives you a bit more time to get into it. This week's chapter is chapter 15, which is about monics and epics, and that's all very exciting. So let's jump straight in. The first questions, there are some questions about the terminology, and these are very valid questions, and the terminology monic and epic at all, monomorphism and epimorphism. And someone said, while epic refers to something that is after, monic seems to refer to the set theoretic property of injective. So I think, I don't know Greek much myself, but upon Googling, I find that epic can mean after, but it also means onto. And I think that's what the point is, that it is really the sort of Greek versions of injective and surjective. Injective meaning one thing. It's like, and that those are the Latin versions of one to one and onto. Although, as I probably said somewhere, I don't like the terms one to one and onto, because I don't think they have the correct parts of grammar, and I don't think that they have the correct sounding meaning either, because I think one to one is used to mean injective, but it really sounds like a bijection, because it sounds like one is going to one on both sides. But the idea is that on the one hand, we have one thing going in, that's kind of one, and that's one-to-one injective and monic, and the other one is onto, that it covers everything, and that's surjective and epic, and that's where those terms come from. So another question is, can the target set depend on the source set? What would that mean mathematically? And the answer is, I don't know that I know what you mean. So the source and target are just sets. They just have to be defined in some way. And even if the target set is defined in terms of the source set, which it might be, then once it's been determined, it doesn't change. So I suppose here's an example. Let me get the whiteboard up. Whiteboard. Oh, I need to just hide the bookmarks toolbar. Okay, that's better. So let me share that screen. So, for example, sometimes what you might have is a function from A to B, and then you want to we sometimes decompose that using an epic and a monic. Did I say that somewhere? I don't know if I said that anywhere. Well, anyway, so what you can do is that you can say, well, this might not be surjective, it might not cover the whole of B. So what you could do is take the part where it does cover, just take the part that it hits, which is the image. And so this is every element f of A such that A is in A. So this is surjective because by definition, it's just a whole load of elements hit by F, but it's also a subset of B, because every element f of A is an element of B. So then you can make an injection like that. And so in this case, we've got a new function here where the target has been determined by the source set. So I don't know if that's the kind of thing that you were thinking of, but that is a possible thing. So someone else says, despite my best efforts, I'm still having trouble with splitting and pre-image. What is the relationship between splitting and pre-image? Does page orientation, reading left to right, make a difference in understanding these concepts? That's a good question. I don't know if it does, but I think that the point about arrows is that they're supposed to work in any direction. So although I prefer writing my arrows going from left to right, if I had drawn this whole diagram like this, I wouldn't be extremely bothered by it because I can follow the arrow and still know that this is going to go like that, and that inclusion is going to go in there. I think that if it helps you to draw the diagrams going the other way, then good. I'm not, so the thing about splittings, and there's another question saying, what is being split when we talk about a splitting? And I suppose, do you know, I've never thought about that because I think of it myself as being a splitting going back, and what was that about? The image in my head is of something being split because we're going backwards. And I think it's to do with the fact that, it may be to do with the fact that when you have an isomorphism, you have a morphism going backwards like that, and then two things need to hold because we need the composite in this direction to be the identity, and we also need the composite in that direction to be the identity. I hope you can see my little mousy thing moving around. And for a splitting, what we're doing is we're separating out the two halves of that definition. So perhaps that's what we're splitting. But I honestly have an image of splitting wood. I feel like that I just have an image of this thing going backwards and splitting it. The relationship between that and a pre-image, I suppose, is that if we're talking about functions between sets, then sometimes thinking about pre-images helps us find a splitting, because if this function is f, then often what we do to find a function going backwards is we want to take everything in B and map it back to something in the pre-image of B, so that when we go around that way, we'll get the identity. But that is a very specific, that's very specific to sets. And so you could think of that as being a basis, a starting point for generalizing to the notion of a splitting. So someone else says, there's a kind of haze that can often set in when I'm studying abstract algebra, where I feel like I start losing track of all the many definitions. That's interesting. I wonder if you have that haze in other subjects, because I feel like every subject has a lot of definitions that come into it, whether it's abstract or not. And so, for example, when thinking about economics, I get very mixed up between whatever supply side means, or the difference between inflation and interest rates, and how you can have an inflation and a recession at the same time. And when thinking about vaccines, for example, I'm constantly getting mixed up between what specificity and the other one is. And I would rather just think of it in terms of false positives and false negatives, or some kind of percentages of exactly what is over what, because I can't ever remember what. Specificity doesn't seem to mean anything to me. So I think that in every subject, there are terminology things that if you're not used to them, they get confusing. But if you are used to them, then they're not confusing. And really the only way, well, the main way to get used to them is to use them a lot. And I suppose that's where one of the, when mathematicians say you have to do examples, I think that you don't have to do examples, but doing examples is one really good way to just get used to the concepts and internalize them, because most of us who do research maths don't believe in memorizing things, because memorizing things doesn't really, first of all, it hasn't helped us, most of us who do research maths, and secondly, it doesn't really get it deep into your consciousness. It sort of gets it superficially into your consciousness. At least those of us who don't get on with memorizing things, that's what we feel. It's possible that some people memorize things and they go deep into their consciousness, but I haven't met any abstract mathematicians who do that. And so for me, I suppose monic and epic, I know that they're related to injective and surjective, and injective and surjective have gone deep into my consciousness over the years. And the definition of monic, because I worked with it a lot when I was doing examples, I got really familiar with the picture of the fork and that being a monic. And so I spontaneously just can kind of feel it. I've definitely not memorized which way around the diagram for a monic is as opposed to an epic. I just did it a lot and then got some deep association for myself. And so if you're not planning to do loads of exercises, then it's much harder to get those things into your consciousness, I think. And I suppose that's why people often say that you have to do loads of exercises. So I think it depends what you're aiming for. And if you're just aiming to see some ideas, then in a way it doesn't matter what any of those words are. You don't have to remember the words. You only have to remember the ideas and the shapes of the diagrams and the concepts, and then you can go back and look them up when you need to. I definitely do not remember the terms retract and the other one, see, I can't even remember it, section. I have no idea which one is which. I can't remember which is a left inverse and a right inverse because I can never remember whether everyone is writing it using the algebraic symbols or the arrow notation. And so I just draw the diagrams. I don't know if that will help. So another question, can you talk a little bit more about equality of morphisms, as in statements such as Fs equals Ft? Are two morphisms that are equal literally the same morphism, or do they simply have the same effects on everything? So this is I think a kind of higher dimensional question. The thing about categories, one-dimensional categories, I suppose I can stop sharing for a second. The thing about one-dimensional categories is that there is no dimension higher than morphism. And so the only thing we can say about morphisms is that they're either equal or not in general. Now, in specific examples, we define morphisms in different ways. And the notion of what it means for two morphisms to be the same comes down to what the definition of the morphism is in the first place. So in general, in a category, morphisms are the same if they're just the same. In a specific example, such as functions, so functions are defined to be the same when they do the same thing on the elements. And so that's not, this question is saying, do they simply have the same effects on everything? Well, the thing is that that's the definition of sameness for functions. So let me just share the screen again. What does it mean for two functions? It's equal. What does it mean for two functions to be equal? So what we've got is two functions. They have to have the same source and target. F equals G means, by definition, this whiteboard is really terrible today. By definition, for all A in A, F of A equals G of A. That's all it means. And so there isn't a difference between whether or not those two functions really are equal or whether they just have the same effect, because having the same effect is what it means for functions to be equal. And so what that means is that even if we write the functions differently, so we might say F of A equals 1, and we might say G of A equals A over A or something. So those look different, but they are literally the same function by definition of equality of functions, because they would have the same effect on everything, provided we can always divide A by A. So the next part of the question says, it's strange to have so many levels of equivalence. I feel like I'm doing something weird when I say that one morphism equals another. That's a good instinct. Maybe that means you want to do higher dimensional category theory. Because if you don't want to say that morphisms equal each other, then we need another dimension in order to say that morphisms can just be isomorphic to each other. And that's why we get into higher dimensions. Very good. Okay, so some more specific questions. Page 196. Could I spell out why F and G are certainly monic or epic? So this appears to be definition 15.7. When I'm talking about if you have a one-sided inverse, then F is certainly monic. So certainly here doesn't mean obviously, it means because it means definitely. But the reason that I say certainly monic is because it's more than monic, because being split monic is more than just being monic. There are a lot of ways to be monic without having a splitting. But the reason it's certainly is because it's as in the proof above. So the proof above showed that if F is an isomorphism, then F is monic. And so the thing is that it didn't actually use the full definition of isomorphism. It only used one side of the definition. And so that's why I then used it in the part below. So in definition 15.7, what we've got is A to B, we have F, and then we have a G going back to A, and the composite this way around is the identity on A. And so the reason it's monic, if you look above in proposition 15.6, that's the reason it's monic, because if you imagine putting two morphisms into here, S and T, then we want to show that if this composite equals this composite, then S has to equal T. And so then we go, if this composite equals that composite, well, then you can go all the way along to G to cancel out that F, and then S does equal T. So it really is just the proof of proposition 15.6 above. The next question, also on that page, why is G called a retraction for F? I think it's something to do with topology. If you look up retraction topology, you'll see what that means. If you haven't come through topology, which I didn't when I learned category theory, then it might mean nothing to you. And then like me, you might never be able to remember what the difference is between a retraction and a section. Okay, next question. Page 201, how is it that we can get a splitting for the absolute value function when normally we might say there's no inverse for the absolute value function? Well, be careful here, because when you said normally we'd say there's no inverse for, so the question said normally we'd say there's no inverse for this function, but you haven't said what the source and target are, and whether you can find a splitting or an inverse for something depends on what the source and target are. So if you're thinking about this as a function from, say, the reals to the reals, then there's definitely no inverse. Or even if you think about it from the reals to the non-negative reals, because the positive and negative of the same value both go to the same place, so you can't invert it because you don't know which one to go to. But even there, if you just went from the positive reals to the positive reals, then that would be an isomorphism because everything would just go to itself. And so, however, in this question, we weren't looking for an inverse, we were only looking for a one-sided inverse, that is a splitting. And so in this case, I was just going from -1, 0, 1 to 0, 1. So if we went from the entire reals to the entire reals, this is not injective and not surjective. If we go from the positive reals to the positive reals, it is injective and it is surjective. Whoops, that's not how you spell surjective at all. If you went from the reals to the positive reals, or do this, so here we've got positive and negative numbers, but we're only going to non-negative numbers. So this one is not injective, but it is surjective. And so we can find a splitting for it, because we can just send 0 and 1 back to 0 and 1. And here is where we can find something in the preimage. I believe that's what happens on page 202. Right. So here is where the splitting, we construct a splitting by finding the pre-images. So what's in the pre-image of 0? The only thing in the pre-image of 0 is 0. So 0 has to go to 0. Whereas what's in the pre-image of 1? Well, -1 and 1 both go to 1. And so those things are both in the pre-image of 1. So when we're constructing our splitting, we could choose, we can send 1 to either 1 or to -1. And so, yeah, there is a case where the splitting and the preimage are related to each other. I suppose another thing to say is that if we aren't some kind of function, then we might not even have a concept of preimage, although there is a categorical way of doing preimages even when we're not functions, but I won't go into that right now. Okay. So the next question, page 200, why is it a left inverse if f is on the right? That's a typo, sorry about that. If you look on the errata page, the definition of split epics after split monics, I did some terrible cut and paste errors, so sorry about that. Next question, page 202, what are examples when you would invoke the axiom of choice and when you would not invoke the axiom of choice? Does this become an emotional debate among mathematicians? So here's the thing, you either need to invoke it or you don't. There isn't any debate about whether you have to invoke the axiom of choice or not. So I guess I can stop the share. You need to invoke the axiom of choice anytime you're in a situation where you've made an infinite number of choices. So for example, if we were going to make a splitting for the absolute value function from the whole reals all the way to the non-negative reals, then we would have to pick something in the preimage for every single element of the reals. And the thing is, we don't actually have to make a separate choice each time, because we can just overall decide that we're always going to take the positive one, and then that doesn't have to invoke the axiom of choice. And so you only have to invoke it if you really have to make an arbitrary choice an infinite number of times. So the classic example that gets done in set theory classes, I think, is the one about shoes and socks. So if you what's the scenario? You have an infinite number of pairs of socks, and the question is, are they counted? Can you line them all up? So for each pair of socks, you have to decide which one to put first. And there's, unless they're, I understand that in Germany there are socks that are labeled left and right, so you can make sure which is which. But if your socks aren't labeled left and right, then you have to keep making an arbitrary choice about which one to put first. Whereas if you're doing shoes, you don't have to make an arbitrary choice, because you can just always decide you're going to do the left one first. And that's only one choice that you've made overall. So there isn't any ambiguity really about whether you have to use the axiom of choice or not. Whether it becomes an emotional debate among mathematicians, I've never seen it become an emotional debate, but everything can become an emotional debate, can't it? Usually I see the axiom of choice being thrown around by people who want to show off something that they know about maths, but they're not mathematicians. And so the two key things I've seen people throw around about that, three key things. There's the axiom of choice, there's Russell's paradox, and there's Gödel's incompleteness theorem. And so I've quite often met people in social situations, usually male people, who want to show that they're cleverer than me. And they try and do that by saying that hasn't Russell's paradox broken the whole of mathematics, or that Gödel's incompleteness theorem shows that mathematics is all wrong, or they say something about the axiom of choice to try and show how great they are. And I think that in all practicing mathematics I've seen, if you need to invoke the axiom of choice, you just invoke it. And you observe, or rather you observe that you need to invoke it. And I suspect maybe it's philosophers or possibly set theorists who worry about it. I don't know if maybe when doing computer aided mathematics, maybe it makes a difference because it might be a kind of thing that computer can't do. But I've never seen it get really emotional. Everyone I know just kind of goes, oh, well, now here we would need the axiom of choice. And it's like, I think I feel like I've said this somewhere, that it's more like just having, when a vehicle is reversing, having something saying this vehicle is reversing, so that everyone knows it's reversing. So if you've had to invoke it, you say you've invoked it, because so that everyone knows you invoked it, and that's that really. Or rather, so that everyone knows it was involved in this proof. And I think it kind of shows that a proof is a little bit more tricky than in some other places. Okay. So then there are a bunch of questions about the example of the natural numbers including into the integers, and that being surjective, it being epic in the category of monoids. And some people found that quite interesting, which I'm glad, because I think it is quite interesting. So someone said, can we think of this monoid morphism as being epic because it is essentially surjective, in the sense that what the function does hit is sufficient to generate the stuff that it doesn't hit? I think that's a pretty good idea. Just, I would say, careful, don't, I know what you mean by essentially surjective, but essentially surjective means something else. That's a specific property that we'll see later that is the correct notion of surjective for the next dimension up. And this isn't about the next dimension up, it's about generating enough things. And so I think that is a pretty good intuition. The last little section on density is about that as well, because it's saying that if you map from a space from a dense subspace into a completion of it, then it's not surjective, but it has covered enough to generate the rest of it. So I think that's a pretty good intuition, at least for all the examples I can think of. Right, so someone else says, do I have the right idea that it's not surjective, but it's sort of basically surjective? It suffices to capture the behavior of the target object. Such that if the function somehow were surjective, you wouldn't learn anything additional about it. It's not so much that if the function somehow were surjective, you wouldn't learn anything additional about it. It's more about functions, the next function afterwards, and about how it doesn't leave what comes after it any choice, because you've covered so much of it already. So then there's a question about the proof. So I'll share the whiteboard again here. The question is about a function from the integers to some other monoid. And it's about why the entire thing is determined by where 1 goes. And the question is, what about inverses? And so so we know, if we know where 1 goes, does this determine where -1 goes? And so the general idea here, and I think it's really important to see what the general idea is and then turn that into a proof rather than trying to go straight for a proof. The general idea is that -1 is the inverse of 1 in the integers, and that if G is a monoid morphism, it has to preserve inverses. And so G of -1 has to be the inverse of G of 1, and inverses are unique. And inverses are unique is something that we proved in the previous chapter. And so what this question says is, I know that G of 1 plus G of -1 must be the identity in M. So you're writing the monoid binary operation in M as plus as well, and have declared that you know that G of 1 plus G of -1 must equal the identity, which is true, but what you haven't observed here is that it must be true the other way around as well. So also because -1 is the inverse both ways around in the integers, this means that this way around also equals the identity. So then if you were going to keep going with this proof, then you could say, so what if there were two possible choices for g of -1? So this has become a proof that inverses are unique. So what we can do is we can say, suppose this is called A. Suppose B and B primed are both inverses of A. So we know that A plus B will equal the identity, right? But then we also know that B primed can cancel out A from the other side, and B primed plus A is the identity. So we add B primed on the left here, right? But then this cancels out because that's the identity. So then we get that, whoops, that was supposed to be an implies sign. So that's the identity. So we get that, and then these identities cancel out. So this implies that B equals B primed. So the upshot is that g of -1 has to be the inverse of g of 1, and inverses are unique, so that does entirely determine it. So the last question is in reference to sub-objects and higher dimensions. I'm trying to understand the difference in ideas between contexts of a general category of morphisms being equal and those in higher dimensions to examine preservation of functoriality versus sub-objects where morphisms are the objects and slice categories. I understand this should wait, if this should wait for later. I think that I'm not sure what you're asking, so I'll just answer something general, which is that whenever you have higher dimensions, so later on we're going to see that there are categories where you have not only objects and morphisms between them, but you also have morphisms between the morphisms, and that's what higher dimensions are. And in that situation, every axiom that holds between morphisms in ordinary category theory can now hold just with an isomorphism in between the morphisms instead. And that isomorphism is at the second dimension. Then, if you have a situation like a slice category, which we haven't got to yet, but if you have a situation where objects are morphisms, then what usually happens is that the morphisms in that category are commuting diagrams. So a slice category C over an object X has objects like that. So X is fixed, and morphisms, you have one object from A to X, and you have another object from A prime to X, and then a morphism will go across here such that this triangle has to commute. If you have two cells floating around because you're in a higher dimensional category, then it would be more natural to ask for there to be a two cell inside here, and then you would get two cells in your slice category as well. So everything would go up a dimension. So whenever you have a commuting diagram or something saying that morphisms are equal, if you had higher dimensions, you would be able to put a higher dimensional morphism in there and say something more subtle. I don't know if that's what you're thinking, but that is what I was thinking after your question. So I think that's all the questions. Thank you very much. Thank you very much for your book club. Thank you for your patience with hash brown, no stupid questions. Yes, I do call hashtags hash brown. Sorry about that. Someone says the videos have definitely been helpful and worth waiting for. Thank you for continuing to create them. Thank you for continuing to watch them. Also, thank you for adjusting the deadline schedule. Okay, good. I'm glad that's helpful. Thank you. Thanks again for asking all our questions. Asking all our questions. Maybe that should be a new verb, to asker. which means that where you answer and ask at the same time. I don't know. Anyway, thank you for following along with the book club. And thank you to everyone at the Topos Institute for sorting out the videos and the questions. So next week, 2 weeks away, we'll start universal properties. Very exciting. And so I look forward to your questions. Bye.